All right, we're here with our honor stats class, period 2, to finish off Tuesday, the first of the month, talking about chapter 9. All right, so you're going to see that pretty much everything we talk about, maybe a few things, but for the most part, we've talked about a lot of this already in doing these examples on Desmos. Okay, so the hope is that over the next couple of days, we can clear up any misconceptions or understandings that you still need a little help with about linear regression, because the test next week is all about linear regression. That's what it's about. Okay? So in the first slide, if you take a look at my red scatter plot, this is the original scatter plot that's looking at the relationship between the duration that a penguin can spend underwater without coming up for air, okay, and the heart rates while they're doing that dive. All right? So if you were to describe this association for this scatter plot in red, you would probably use the word negative, strong, but you'd probably most likely put curved. Now, if you don't see that bend, that curve, when you look at the residuals plot, you might be able to see it a little more clearly. Okay, so this is just showing you that, say you think it's linear, so you do everything, that's why we always check the residuals plot to make sure that I should hope to see in the green dots no pattern. Right? The green dots, the residuals, are supposed to be showing me nothing going on, a cloud, no pattern, but that's a curve. No, that's a curve. Okay, so we would say that this scatter plot here, in terms of linear regression, it's not appropriate to use that model. So this would be not appropriate. Not appropriate to use the linear model. So I was trying to say, Edgar, that if you look at the red one, I think there's a curve, but not everyone might see that, right? Jarvis said initially that was linear, right? Because it kind of looks close to linear, but there is a curve. But if you think it's linear, Edgar, you would actually run the linear regression, right? You'd make the model. But then when you check the residuals plot using Desmos, you would see that there's a pattern in the residuals plot, which means it's not appropriate to use the linear model. That's the linkage I need you to know before Thursday of next week. All right, before it counts for a very large grade. What's that? Yes, we have a test already. We had a test a couple weeks ago. You were there, Charlize. Okay, any questions so far about looking at residuals plots? Okay, let's go to the next slide. Now, sometimes when you look in the residuals, you might actually see that there's multiple groups happening. All right? If you notice, whether it's in a scatter plot or in the residuals plot, that you've got multiple groups, the best idea is to actually just split them and do 2 different things for everything. 2 different scatter plots, 2 different models, 2 different residuals plots. Okay? One example that comes up from time to time when I'm looking at, when I'm watching some TV is someone will be looking at a relationship between a football team and some stat. All right? And they lump all the football players together. Right? I think one of them was talking about the weight of a football player. Well, the weight of someone who's playing on the offensive line or the defensive line is going to be significantly different than the weight of someone who is a skill player, a position player, like a running back, halfback, quarterback. So I would not really want to look at those together. I'd want to separate them and look at them separate. That would actually mean something to me as opposed to together. Okay? For example, here's a useless stat I saw last night. All right? Last night I was watching a little bit of Monday Night Football because then it got really boring. Anyway, so I was watching football, and if you don't have to know anything about football, but there's a kicker on every team. Okay? And the kicker is responsible for literally kicking the football through the goalposts. Okay? So before one of the team's kickers went to kick a field goal, they put a stat on the TV. All right? And the Steelers were playing the Bengals. And the stat was for the Steelers kicker that this kicker is 6 for 6 when his team is playing the Bengals. So he kicked 6 field goals, and made all 6. And as someone who's in stats, do you think there's a relationship between a kicker and how often they make field goals and the team that they're playing against? Yeah. You think so? Yeah. Why would you say that? Momentum, confidence, are those quantifiable? So are they a good field goal block? How many times have you seen a field goal be blocked in the NFL? Not often, right? Very rare. Right? Okay, I'm talking about the NFL, Edgar. High school, it happens all the time, right? What I'm trying to say is what would be more meaningful to me would be how good is this kicker from this distance? Because in my mind, what's the thing that matters the most when a kicker is kicking a field goal? How far away they are. That's all I care about. How good is this kicker from 40 yards? That means something to me. But to say that they're 6 for 6 against the Bengals, cool. That doesn't really help me. That just tells me that this person has kicked 6 field goals against the Bengals. Excellent. Anyway, it's just something that came up last night. And, it doesn't bother me. All right, so I've used this word extrapolation before. Do you remember when I used this word extrapolation last week? Who remembers when I used it?
Me.
When did I use it? How did I use it?
You said that we talked about it.
Fair enough. All right, we'll have to go check the tape. Now, we're using it now because when I used it last week, it was when we did the Toyota Corollas. Remember that problem with the used? Are you okay, Sal? Okay, thanks. So with the used Toyota Corollas, one of the questions asked, what if the Corolla was 20 years old? But our data only went from 1-year-old Corolla till I think it was like a 13-year-old Corolla, something like that. So 20 is outside of our data values in terms of our explanatory variable. So anytime you're moving past that in either direction, that's called extrapolation. All right? And I'm not saying you can't do it, I'm just saying you shouldn't do it. You might run into some type of issues because things might change, right? In terms of trying to figure out whether your investment portfolio is going to be successful in 5 years or 10 years, things are going to change, all right? Around the world, it's going to cause your investments to go up or down, okay? Any questions on extrapolation? So just be careful when you're doing that, aka don't do it. Okay, the next slide. Outliers, leverage, and influence. Now, I know yours is not in color, but if you look at my scatter plot on this slide, you'll see all of those dots in blue and a blue line, and then you'll see a red line and one red dot. This one red dot here, if I put it into this scatter plot, causes the linear model to move that much. I know you don't think that looks significant, but that's a significant move when it comes to the slope of a linear model. Okay? So any point that's causing the slope to change is called an influential point. All right? Any point that's in your scatter plot that causes that much change, that the slope has changed that much, you would call it influential. So what you would most likely want to do, if you have something like that, is to run it with it and without it. Run the linear model with the point in your data values and then take it out and run it without it and see if it's that much different. All right? This also applies to any outliers. You may not think this is an outlier, this red dot, because look at the x values. You see how it's almost like a little bit to the right of the middle, but it's not the farthest one to the right. So you may not even see that it's an outlier until you start to look at the scatter plot of it. Okay? So just be careful on that. I think a lot of us think, oh, only outliers are going to mess us up. It's not just outliers. Questions? So this point, you might not consider it an outlier because it's not the farthest. It's not like way over here, right? The dot isn't like way over here, where you'd be like, oh, that x value is way far away. The x value is within our range of x values, but the y value is so much higher that it's causing the line to change so much, we call this an influential point. And any point that causes that much change in my model, Leslie F., I'm going to run it twice, with the point and without the point. Okay, let's go to the next one. Here's another example. I took this from the textbook, which is probably too old at this point for you guys to know, but it's talking about the shoe size of a person and their IQ. Okay, so if you read the chapter, there was a little snippet on that. And this red X on my screen is Bozo the Clown. Do you guys remember Bozo the Clown? Some of you probably do. Maybe not everyone. Anyway, Bozo was this not creepy, super creepy clown that would have like this kids show, and they would play games and stuff on the show. All right, I used to watch it when I was 7, so it was a long time ago, early 90s. All right, and it was really popular more in the 80s, late 80s. Anyway, they're showing you that if you have Bozo here, and Bozo is really smart, a high IQ, he is a clown and has a very large shoe size. Okay, and watch what happens when you put that red X in. Now the model almost seems positive. But if you said Bozo scored very low on the IQ test, now the model is saying that it's negative slope. So again, we would say that Bozo is influential, causing that slope to change. Because if you took out that red X in both of those scatter plots, you would probably say it's just a cloud. And I think you would all agree that your shoe size, if we're talking about adults, your shoe size has nothing to do with your IQ. You agree? Yes, I assume you agree. Yes. No? Okay. Any other questions about this slide? Almost there. 2 more to go. Now, one thing that can be difficult to spot are these influential points, because if the point is causing the line to get closer to it, all right, I taught you guys last week that the residual is the difference between your observed value, so your actual value, and your expected value from the model. So if the influential point is causing the line to be closer to it, it's actually reducing the residual. So sometimes it can be difficult to spot them because it might have a small or medium-sized residual. Okay, so if you go back to Bozo, don't worry, I'll come back. If you go to Bozo, you see how Bozo actually is not that far away from the line on both of these? All right? So that would mean that the residual isn't that large, so you might not even see that that point is causing that much influence. Okay, so that's what they're reminding you here. It was a clown. He's a clown. It's a joke. He doesn't actually. I don't know which. I don't know what's Shaq's shoe size. Should we Google it? It's 18. Mr. Earls is a 15.
Oh my God.
I'm pretty sure I remember he's a 15.
I think Yao Ming was 22. Yeah,
Yao Ming was a 22. I mean, there are people that are over 7 feet tall, so in theory, they're going to have pretty large feet. Okay. The next part of this slide is reminding you again about causation. You might be doing a problem that has a very strong linear relationship, and even your R squared is really close to 100%. You might be thinking, man, what an amazing model I'm looking at. But be careful. You always need to be cautious, because just because you have a strong correlation does not mean that you have a cause and effect relationship. Okay? So please do not say yet that something causes something else because you see this strong relationship. Don't do it. Okay? We're going to talk in our next unit how you have to actually run experiments to get to that level. Okay? And we're not doing that yet. We haven't even started talking about it. Okay. Now, we're going to talk about this later in an example, but here it is right now. So, summary values. If you are looking at in one of your classes here, or maybe in college, or maybe your job, if you're looking at a scatter plot or some kind of data, representation, and you see that you're working with averages. Be cautious when you're working with averages, because it's going to make you think that the relationship is stronger than it actually is. Okay? So when you're working with averages, it's going to make you think the relationship is stronger than it is. It's going to have less variability. For example, here are two scatter plots. The one on the left has every, I think this is the height of, yes, the height of men explains their weight. This is every man in their study. And then this one was averages. And if you look at the difference, you can see that the one that has averages looks really strong. Okay, that's a very strong relationship. Here is a little more scattered. Okay, so it's misleading when you work with averages. If you get to that point in your job or something and you've got averages, ask wherever you got the data, hey, can you give me all the data values? You'd much rather be working with all the data values.
Is that because it's more specific?
It basically takes anything, Jarvis, that's farther away from the middle, and it just kind of shrinks it. All right, because anyone, if you take, let's say we're talking about all 550 students here, give or take, at our school, and we looked at all of the heights. Okay, so everyone's height, I wrote it down in inches. And then I said, okay, Jarvis, instead, I want to go to every classroom during second period and find the average height for that class, average height for this class. And so instead I'll have what? 25, 30 heights. It's going to look much more tight in terms of the spread. I just crushed that one. Man. Sometimes you just have that moment, right? We just get it. Oh. Questions? No? Okay.